Here I have a very brief image of an engine from the transfer side. So these, so we've seen the cam shafts of the engine when we open the valve gasket to replace the valve gasket, and that's over here. These are the cam shafts. So your air and fuel enters from this chamber, and when the intake valve opens, this air and fuel mixture enters the combustion chamber, and this is the piston. We've seen the image of how this piston head looks like in those videos, and this piston compresses the fuel and air mixture, and our spark plugs ignites this mixture, which would expand the air fuel ratio once it starts combustion. When it starts combusting, this piston is pushed down. This piston is pushed down, and then it creates a power stroke at this crank. And once everything is combusted, it will again push it up. This valve opens, the exhaust valve, and your exhaust goes out. Okay, so for an optimum kind of combustion, we'll have to see how much of gasoline should be added for how much of air. I mean, that's the reason we wanted to make sure our air and fuel system is particularly clean and working optimally. So let's just see how this thing works. So we have gasoline, which is chemically octane, C8H18. We have air with around 98% nitrogen, 21% oxygen, and around 7.7% argon and other gases. But for simplicity, let's consider 79% nitrogen and 21% oxygen, or 3.76 times nitrogen for every molecule of oxygen. So in our combustion, let's make the formulation C8H18 plus O2 plus 3.76 times nitrogen. This would give CO2 plus H2O, and you get nitrogen, which is not required for trying to understand this equation. Let's try and balance this. So 2, 25, 16, 18. This is how it's balanced. And so for every molecule of the octane, we need 12.5 molecules of air, if that makes sense. Let's see by weight how much this would be. So we want to see air to fuel ratio. So air is 25 times. The molecular weight of the atomic weight of oxygen is 16. There are 2 atoms per molecule, plus 25 times 3.76 times atomic weight of nitrogen, 14, times 2 atoms over 2 of the atomic weight of carbon is 12, and there are 8 carbon atoms, plus we have 2 times of atomic weight of hydrogen, 1. There are 18 of them. this comes to 14.89 is to 1. But since we did these approximations, technically what the industry standard believes is it is 14.7 is to 1. So this is your air fuel ratio. So that means that's stoichiometric at psychometric value. You need 14.7 parts of air for 1 part of gasoline for optimal combustion, so that you don't have any more nitrogen. So you need 14.7 parts of. So what we can conclude here is we need 14.7 parts of air for 1 part of fuel, so that the combustion, the post-combustion exhaust doesn't contain any more octane or air in it. In the next video, we'll try and learn how do you read these data from our car to know its condition. What do you mean by when it is running rich or lean? And stay tuned on my channel to know more about cars and